Hello everyone. In the previous class we discussed about prime element, prime ideals, irreducible elements and also coprime. Now we'll continue the discussions with today we're going to talk about Euclidean domain and principal ideal domain. What is meant by Euclidean domain? An integral domain is said to be an Euclidean domain if there is an integer valued function d defined on the non-zero values of R satisfying these conditions. D value of any element of R minus 0 will be always non-negative, and D value of AB is greater than or equal to D value of A for any non-zero elements of R. And the third condition, it satisfies the division algorithm. That is, if A and B are any two values of R and B is a non-zero element, then there exists quotient and remainder of division, say Q and R, in R such that A can be written as B into Q plus R, where either remainder is 0 or D value of R is less than D value of B. Then this D is called as Euclidean function. Now again, give an example. We knew that Z is an integral domain and define a Euclidean function as follows. D of A is modulus of A for all A belongs to Z. Modulus is always non-negative, so first condition is satisfied. And modulus of AB is always greater than or equal to mod A. And the third condition also is true by division algorithm for integers. So all the conditions of Euclidean domain are satisfied, therefore Z is an Euclidean domain. And similarly, we know that any field F is integral domain, and define the Euclidean function D as this. And with this, obviously these three conditions holds, therefore any field F is a Euclidean domain. Given exercise, you just work it out. Show that the set of all polynomials f of x over the field F is an Euclidean domain with the Euclidean function D, which is an integer valued function defined as D of f of x is nothing but degree of f of x for all non-zero polynomials. You write this one as an assignment. Now, after this we are given proportion. What it says, this proposition, the ring Z of I of Gaussian integers is a Euclidean domain. What is Z of I? Z of I is collection of all elements of the form A plus IB, where A and B are coming from Z. We knew that Z of I is an integral domain, and the units of Z of I are plus r minus 1 and plus r minus I. To show that this is an Euclidean domain, already it is an integral domain, so we have to show these three conditions holds good for an integer valued function. So we need to define a Euclidean function which is an integer valued function which satisfies all these three conditions. Now let us define a function D as D of A plus IB, where A plus IB is an element from Z of I, is nothing but n of A plus IB. This n is a mapping which is of the form, earlier we have defined a mapping n from z of square root of minus 5 to z by n of a plus b root minus 5 is equal to a square plus 5b square. In the same manner, we are defining the mapping n from z of I to z by n of a plus ib is equal to a square plus b square. For all a plus ib belongs to z of I. Now clearly d of a plus ib, which is sum of the squares of these numbers, a and b are integers, and since we are squaring it for any integer, the sum of a square and b square can never be negative, therefore this is non-negative, therefore it is greater than or equal to 0. And further we should note that d value of a plus ib is 0 provided a is 0 and b is 0. Otherwise, sum of these two non-negative value can never be 0. This is 0 provided a is 0 and b is 0. Because we are going to square it for any positive or negative value, a square and b square both are positive. Sum of positive value will become 0 provided a is 0 and b is 0. So a and b are 0 means a plus ib will be 0. So that means if d of this is 0 if this is 0. But suppose if a plus ib is non-zero, then d of a plus ib is always greater than or equal to 0. So we have proved the first condition of Euclidean domain. Now let's prove second condition. What is that second condition? Let us assume x and y are any two elements of z of I. But any element of z of I must be of this form: a plus ib and c plus id. Both are non-zero. And d of xy, we know that d of xy is x is a plus ib, y is c plus id. This is nothing but x into x bar, y into y bar. So that we are going to get, because you know you have defined d of a plus ib as a square plus b square. What is a square plus b square? I can write this one as a plus ib into a minus ib. A plus ib into a minus ib is a square plus b square. Since your x is a plus ib, so you're going to get a square plus b square here. So this is a plus ib into a minus ib. This is c plus id into c minus id. So that their product is a square plus b square into c square plus d square. But what is your a square plus d square? This is d of x. What is your c square plus d square? This is d of y. D of x into d of y. This is obviously product of two numbers will be greater than or equal to one number. You are multiplying d of x by d of y, which is obviously greater than or equal to d of x. So we have proved d of xy is greater than or equal to d of x for all x and y belongs to z of I minus 0. So second condition has been proved. Now we'll prove the third condition, that is division algorithm. Suppose x and y are into values of z of I and y is a non-zero element. Now we knew that z of I is not a field. What is the field of quotient of z of I? It is q of I, because field of quotient of z is q. Similarly, field of quotient of z of I is q of I. Therefore, the multiplicative inverse of y need not exist. Will not exist in z of I, but it surely exists in q of I. Therefore, x by y, that is x into y inverse, x by y, which can also be written as x into y inverse, belongs to q of I. But any element of q of I must be of the form u plus ib, where u and v belongs to q. So since we are saying this is an element in q of I, it must be of this form. So let's assume this product x into y inverse is equal to some s plus it, where s and t are elements of q. But remember, your s and t are rationals. Now let us assume that m and n are nearest integers to s and t. So your m and n are integers which are nearer to s and t. M is near to s and n is near to t. Because you know, between any two integers there exists infinitely many rationals. So that is the reason, since m is near to s, their difference cannot be more than half. It should be less than or equal to half. Because, say for example, if you take any rational between 1 and 2, say m is a rational between 1 and 2, then either 1 is near to m or 2 is near to m. You have to choose 1 or 2 depending on their distance, such that the distance between 1 and m, distance between 1 and s is a rational. Don't take m. In your case, m is integer, so s is rational. So take 1 and 2 in between s. So either 1 is near to s or 2 is near to s. You have to choose in such a way that the distance should be less than or equal to half. And similarly, this distance between n and t is less than or equal to half. Now we have written x into y inverse as s plus it. This s plus it can be written as m plus in plus s minus m plus I into t minus n. See, minus m plus m cancels. In minus in cancels. So you will get s plus it only. So we have added and subtracted m and in. We have rewritten this one. Now, because y has a multiplicative inverse, post multiply both sides by y. So that y into y inverse becomes 1. So you will get x into 1 is x. Y into this is, by distributive law, y into m plus in is m plus in into y. And this is s minus m plus I into t minus n into y. Now, let m plus in is equal to q. Because your m is an integer, n is an integer, m plus in, I'm assuming it as q. You should note that m is integer, n is integer, therefore m plus in is an element in Z of I. So your q is an element in Z of I, and s minus m plus I into t minus n into y, which is equal to r. But here we should note that our x becomes m plus in is q, so q into y, and this is r. So your x will be equal to q into y plus r. Therefore your r will be equal to x minus qy. You should note that your x is coming from Z of I, y is coming from Z of I, and we have said q is also coming from Z of I. So x comes from Z of I, q comes from Z of I, y comes from Z of I. By closure law and multiplication of rings, q into y belongs to Z of I. Their difference also belongs to Z of I, but their difference is nothing but r. Therefore, r also comes from Z of I. That means we have proved that there exists r and q coming from the ring. That is the condition they had given. Quotient and remainder should come from the ring. So we have written that q and r are coming from Z of I. We have written x as q into y plus r, where q and r coming from Z of I. Now we left out with the last condition, that is we have to show that remainder r is 0 or d value of the remainder is less than d value of the divisor. Now here in our case the divisor is y. Divisor is y. So we have to show that d of r is less than d of y or r equal to 0. If r equal to 0, there is nothing to prove. We are through. So let's assume r is not equal to 0. If r is not equal to 0, then what is your d of r? D of r is equal to d of, what is your r? We have assumed that r is s minus m plus I into t minus n into y. Now we know that d of xy is equal to d of x into d of y. So because of that reason, d of this into d of y. But d of this is of the form d of a plus ib. What is your d of a plus ib? A square plus b square. Here instead of a, you are having s minus m. So s minus m whole square plus t minus n. This is n, not m. T minus n whole square into d of y. But we know that what is the distance between m and s? Distance between m and s, m minus s or s minus m, because there is a modulus, both are one and the same, is less than or equal to half. Therefore, if you square on both sides, this becomes simply s minus m whole square is less than or equal to 1 by 4. This square of this also gives you less than or equal to 1 by 4. So s minus m whole square is less than or equal to 1 by 4 plus n minus t whole square is also less than or equal to 1 by 4. This is less than 1 by 4. This is also less than 1 by 4. So 1 by 4 plus 1 by 4 into d of y. But that is nothing but half dy. Which one is greater, dy or a half dy? We knew that d of y is 1 times dy is greater than half dy. So we have proved d of r is less than d of y. That means we have proved that there exists q and r in Z of I such that x can be written as qy plus r with d of r less than d of I. Therefore, all the conditions of Euclidean domain are satisfied and Z of I is an Euclidean domain. Now we had given definition. An ideal, domain which is an integral domain is called as principal ideal domain provided all ideals of this integral domain are principal ideals. So we knew that Z is an integral domain and all the ideals of Z are principal ideals. Therefore, Z is a principal ideal domain. Now, there is a theorem which says that every Euclidean domain is a principal ideal domain. We'll prove this one. The given hypothesis is Euclidean domain. And we have to show that it is a principal ideal domain. So let's consider ideal. Let's say I, which is a non-zero ideal, because if it is zero, there is nothing to prove. Zero ideal is generated by zero ideal. So if I equal to 0, then we can write that one as I equal to principal ideal 0. So that ideal is principal, therefore it is principal ideal domain. So that's why we are considering non-zero ideal. Let I be a non-zero ideal of Euclidean domain R. Then we have to show that this ideal is a principal ideal, so that every ideal of R becomes a principal ideal. Therefore, this will become a principal ideal domain. Now, we have to show that I is a ideal generated by A. Therefore, this becomes a principal ideal where A is a non-zero element of I of minimum D value. Now, let's say A is an element in I such that A is non-zero and D of A has least value. Who is assuming this? We ourselves. Why this is true? Because we know that D value of each and every element of I other than 0 is greater than or equal to 0. So they are all bounded below by 0. Hence, all D values are greater than 0 means there must exist a element A with the smallest D value. So that's why we can choose that D of A is the least D value. Now we claim that I is nothing but principal ideal A. Okay, let's prove this one. See, we should note that the smallest ideal which contains A is principal ideal A. But we are saying that A belongs to I. Therefore, the principal ideal A is subset of I. If you want to show that any two sets are equal to each other, we have to show that they are subsets of each other. So, from this, if A is in I, we know that the smallest ideal which contains A is principal ideal A. Therefore, an element of principal ideal A is belonging to I. Therefore, principal ideal A is subset of I. This way is true. So, what remains to show is we have to show that I is subset of principal ideal A. Now, how you are going to show one set is subset of another? Let's say, and let us choose an element X in I, and we show that X also belongs to principal ideal A. That gives us that I is subset of principal ideal A. Therefore, I will be equal to principal ideal A. Therefore, every ideal of R is a principal ideal and true. Now, since X is in I, and we knew that I is an ideal of a Euclidean domain, therefore, every element of I is also present in R. Therefore, we can apply division algorithm. By division algorithm, we can write X as A into Q plus R, where Q and R are any two elements of R with R equal to 0 or D of R is less than D of A. Now, what is your R? Your R is equal to X minus AQ. You should note that your X is coming from I and A is coming from I and Q is coming from R. By the definition of ideal, any element of ideal into an element of a ring should always come in I. A is an element in I, Q is an element in R. Therefore, an element of ideal into an element of ring comes in I. Therefore, AQ comes in I. X is already present in I. Therefore, by the definition of the ideal, the difference will also come in I, since I is an additive subgroup. Ideal means it is the first condition is additive subgroup. Because of that reason, this difference comes in I. Therefore, R is belonging to I. Now, here we are having a condition that either R must be 0 or D of R must be less than D of A. So one of these two must hold. Suppose, for the time being, suppose if r is not equal to 0, then by this definition dfr must be less than dfa. But this is not possible. Why? Because a is chosen in such a way that dfa has a least value. Anything which is less than dfa is not possible, cannot be present in I. But your r is present in I and dfr is less than dfa. But this says that a is the only element in I which is having a least d value. So dfr cannot be less than dfa. Therefore our assumption is wrong. That means r cannot be 0 is wrong. Therefore we left out with r equal to 0. If r equal to 0, then x will be equal to simply a into q. Now it is a multiple of a. Anything which is a multiple of a comes in principal ideal A. Therefore your x belongs to principal A. Principal ideal A. So we have proved that x, which is an element in I, is also present in principal ideal A. Therefore I is subset of principal ideal A. Earlier we have proved that principal ideal A is subset of I. Because of these two results, your I will be equal to principal ideal A. That means we have shown that every ideal of R is a principal ideal A. Ideal is a principal ideal. Therefore, this Euclidean domain is a principal ideal domain. So in general, we have proved that every Euclidean domain is a principal ideal domain. What about, we had given a remark. What about z of x? You should note that z of x is not a Euclidean domain. Why? Because we knew that the ideal 2fx, the ideal generated by 2x, in the earlier class we have proved this one, that the ideal generated by 2x is not a principal ideal. Therefore z of x is not a principal ideal domain. If it is not a principal ideal domain, then this cannot be a Euclidean domain. Because if it has to be a Euclidean domain, then it has to be a principal ideal domain. Now, we had given exercise, just work it out, show that the set of all polynomials over field f is an Euclidean domain whenever f is a field, and show that every irreducible element is a prime element in any PID and hence in a Euclidean domain. Show that a principal ideal domain, in a principal ideal domain, GCD exists. After this, we are having a proposition. Suppose if R is a Euclidean domain and A and B are any two non-zero values of R, and D is the last non-zero remainder in the successive divisions of A and B in this fashion. So when you divide B from A, we are going to get B is equal to A into quotient Q0 plus R1. By division algorithm, we are writing this one with D value of R1 is less than D value of A. Now, after this, when you divide your A from R1, your R1 is your new divisor, then we can write A as R1 into new quotient Q1 plus new remainder R2 with D value of R2 is less than D value of divisor R1. Now choose your R1 as dividend and R2 as divisor. Then we are going to get quotient Q2 and R3 new remainder with the D value of remainder, new remainder is less than D value of divisor R2. Go on, proceed like this. After certain steps, your remainder will become 0. So we are getting Rn minus 1 equal to Rn into Qn, the last non-zero remainder. This is your D according to them. D equal to Rn. Then we have to show that this remainder is the GCD of A and B. And the ideal generated by A and B is principal ideal D. That is, D can be written as a linear combination of A and B. That is, D equal to some lambda A plus mu B, where lambda and mu are any two elements of R. Now, let's prove this one. We knew that d value of A is greater than d value of R1. But d value of R1 is greater than d value of R2, etc. You are going to proceed like this. So d value of A is greater than or equal to all these, which is greater than or equal to d of Rn. So it is a decreasing sequence of non-negative integers. That's why, since it is a decreasing value of non-negative integers, such a smallest, the last non-zero remainder exists. Now, since they are given that R is a Euclidean domain, and we knew that from the previous theorem that every Euclidean domain is a principal ideal domain, let us assume that I is a ideal which is generated by A and B and is a principal ideal. Let's say I is equal to principal ideal X for some X belongs to R. Then we have to show that X is the GCD of A and B. Now you know that this ideal I contains both ideal A as well as elements of ideal A and elements of ideal B. Therefore, ideal A, the ideal generated by A, is subset of I, but I is nothing but principal ideal X. Therefore, what is the smallest ideal which contains A? We knew that it is principal ideal A. Therefore, A belongs to this. A belongs to this, but this belongs to this. But these two are equal. Therefore, A belongs to principal ideal X. But any element of principal ideal X must be of the form X into some number. So your A can be written as X into some number. But by divisibility property, A equal to X into some number means X divides A. Similarly, the ideal B belongs to I, but I is nothing but principal ideal X. But we know that the smallest ideal which contains B is principal ideal B. So B belongs to principal ideal B, which is contained in principal ideal X. Therefore, B equal to X into some number. That implies that X divides B. So we are getting that X divides A and X divides B. This is the first condition for GCD. If you want to say some number as a GCD, then it has to divide both A and B. So your X is dividing A and X is dividing B. Now we left out to prove the second condition of GCD. That is, suppose that Y is another common divisor of A and B. That is, Y divides A and Y divides B. If Y divides A, then A will be equal to Y into some number. But any multiple of Y is present in principal ideal Y. Therefore, A must be present in principal ideal Y. But the smallest ideal which contains A is principal ideal A. Therefore, principal ideal A must be subset of principal ideal Y. Similarly, Y divides B means B will be equal to Y into some number. But any number which is a multiple of Y into some number must be present in principal ideal Y. Therefore, B belongs to principal ideal Y. But we knew that the smallest ideal which contains B is principal ideal B. Therefore, principal ideal B is contained in principal ideal Y. So we have proved principal ideal A is subset of principal ideal Y, and principal ideal B is also a subset of principal ideal Y. Therefore, principal ideal A plus principal ideal B must also be present in principal ideal Y. Therefore, principal ideal A plus principal ideal B, which is nothing but I, is contained in principal ideal Y. But I is nothing but principal ideal X. So we have proved that principal ideal X is contained in principal ideal Y. But the smallest ideal which contains X is principal ideal X. Therefore, X belongs to this, but this is belonging to this. Therefore, X belongs to principal ideal Y. But any element of Y must be of the form Y into some number. Therefore, X will be equal to Y into some number. But this implies that Y divides X. So this is the second condition of GCD. That if there is any other common divisor, then that common divisor should divide the GCD. So here we are proving that X is the GCD. So X is satisfying both the conditions, that X divides A and X divides B. And if Y divides A and Y divides B, then Y divides X. Therefore, X is the GCD of A and B. But we knew that from the successive divisions of A and B, your Rn is also GCD. Therefore, your x must be equal to Rn. That is, D is equal to Rn, which is the GCD of A and B. But since D is the GCD of A and B, in the previous class, in that remark, we had given if this is the GCD, then the smallest ideal generated by D is ideal generated by A comma B. Therefore, D, the smallest ideal which contains D, is principal ideal D. Therefore, D belongs to this. But D is also belonging to ideal generated by A and B. Therefore, D will be equal to lambda A plus mu B for some lambda and mu. Also, lambda and mu can be obtained by using successive divisions which they are given here. How? D is equal to Rn, but Rn is nothing but Rn minus 2 minus Rn minus 1 into Qn minus 1. So here this will be your A lambda plus B mu. If you go on substituting in the reverse fashion, you'll get lambda A lambda plus B mu. So this completes the proof. Now we had given example to show that these two are co-prime in Z of I using the method which we have used in the earlier proof, that is in this result. So let's prove this one. Now divide. We knew that by division algorithm, if one divides another, then we can write in this fashion. Now, let's divide A7 plus 2i from 3 minus 4i. This is your AB inverse. So 7 plus, multiply and divide by conjugate of the denominator, then you're going to get this value. So your AB inverse equal to 13 by 25 plus 34 by 25 into I. Now we'll use the result which we have used to prove. We'll use that method which we have used to prove that Z of I is an integral Euclidean domain. This method, we'll use that method here. Now you know that you got 13 by 25 plus 34 by 25 into I. This is your AB inverse. Let's say this is your S and this is your T. Now, so let's consider the nearest integers to 13 by 25 and 34 by 25. 13 by 25 is less than 1 and 34 by 25 is more than 1 but near to 1. So let's assume M and N as 1 because they are the nearest integers such that their difference is less than or equal to half. So there in that result we have written Q as M plus IN. So your quotient will be 1 plus I and your R is equal to A minus BQ. What is your A? Your A is 7 plus 2i minus, what is your divisor B? 3 minus 4i. What is your quotient? 1 plus I. If you multiply and subtract these two, you will get 0 plus 3i. So your remainder, the first remainder is 3i. So your A is equal to BQ plus R, which is this. Now, by division algorithm, again you divide this one. So by taking your new divisor as 3i, and your new dividend is 3 minus 4i. So 3 minus 4i divided by 3i on multiplying dividing by conjugate of the denominator, you will get minus 4 by 3 minus I. Now we have to choose, this is your new S and this is your new T. Your new S is minus 4 by 3 and new T is minus 1. So let's construct a new quotient Q1, which is M1 plus IN1. This value is minus 4 by 3. Near to this is minus 1. And this is minus 1. That itself is an integer. So your N1 is minus 1 itself. So you're going to get minus 1 minus I. Here our values were nearest integer 1 and 1. Here minus 1 and minus 1. They are the nearest integers such that these two are less than or equal to half. Now, what is your new quotient R1? Your R1 is equal to, your dividend is 3 minus 4i, B, minus, remainder is 3i, new quotient is minus 1 minus I, This will give you R1 equal to minus I. Now what is your B? Your B will be equal to RQ1, if you send this one to this side, RQ1 plus R1. That is, B is 3 minus 4I, which is equal to 3I into minus 1 minus I plus minus I. Now again continue that division process. But we know that minus I, clearly this is your new divisor and this is your new dividend. I divides I, so you're going to get the integer remainder as 0. So straight away we can write this one. Your 3I is equal to new divisor is minus I, quotient minus 3 plus 0. So since this remainder is 0, according to this theorem, if the remainder is 0, the last non-zero remainder is the GCD. So by that theorem, the last non-zero remainder is minus I. That is our GCD of 7 plus 2i and 3 minus 4i. But you are saying that GCD of these two numbers is minus I, which is a unit in Z of I. The values whose GCD is a unit are coprime. Therefore, these two are coprime in Z of I. Thank you.